kernel. But once we know the algorithm, once we know the concept of the rootkit, we can always write a detector. Sometimes we have some problems with reliability of those detectors for some obscure reasons, for some different reasons. But usually, theoretically, it is once we know the concept, it's trivial to write a detector. So, for example, DeepDoor, the rootkit that I presented half a year ago, modified some NDIS data structures, some function pointers inside data structures, but again, it was completely undetectable over the time. But again, once we know the concept, once we know which pointers are modified, we can detect it. And also, I believe that there is only finite number of ways how we can actually implement any given malware. Like if we consider network backdoor, there probably will be like 3 dozens of ways how we can do this, like hijacking NDIS code, hijacking NDIS pointers in many different ways, like we've seen in Alexander's presentation. We can do this in really, really different ways, but not infinite ways, not infinite number of ways. But anyway, once we know the concept, we can detect it, which is so boring. So now imagine a malware which doesn't rely on a concept to remain undetected, which cannot be undetected, which cannot be detected even though its algorithm is known. So how it works? So it's made publicly available, and we can go even a step further and imagine malware which would be undetectable even if its code is made public. This is something which reminds me of a modern crypto. We know the crypto algorithms, but we cannot decrypt the message, right? The idea behind Blue Pill is to exploit SVM extensions of AMD. Actually, the idea is very similar to what Dino presented just a few hours ago, but he did it on Intel VT, and I did it on SVM. So the idea is to provide very thin hypervisor, which will control the OS, and hypervisor will be responsible for intercepting any interesting events. And which events will be interesting depends what actually we want to implement. Keylogger, kernel backdoor, whatever. SVM, Secure Virtual Machine Technology, also known as Pacifica, it was introduced on May 23rd. No, it was not. It was released. So the first processors were available on the market, at least theoretically, on May 23rd. I managed to buy them during the first week of June in Poland, so they were probably available much earlier somewhere else. And the processors which support SVM are all the AM2 socket processors. And these are the only AMD processors which support SVM. Okay, so this AM2 hardware is available, but for example, I didn't manage to find any laptop with SVM technology, which results that I will not be able to show live demo of Blue Pill, which is a pity because I'll tell you later why. I'll just show you a demo movie. So SVM is a set of instructions which can be used to implement virtual machines on AMD 64. And there's a MSR register which is called EFER, which is for many different things, but it has bit number 12, and this bit, when set to 1, enables SVM mode. It doesn't mean that once we enable this bit, we are becoming hypervisor. It just means that the SVM instructions are available for the processor. And you can find detailed reference in Architecture Programmers Manual, Volume 2. Okay, so this is how SVM works. This is the official explanation of SVM. Can you see the cursor? Yeah? So first we have SVM disabled, so there is no notion of host or guest, but still we are the native machine here, right? We are executing some instructions. And then we decide to create a virtual machine. So first we create something which is called VMCB, Virtual Machine Control Block, which consists of 2 parts. One part is the state of the guest, and the other part is the control block. And the state contains information like RIP register, RSP register, segment registers and all the other state which would be necessary to create virtual machine. And control block contains information about what kind of events you would like to intercept. For example, that you would like to intercept every call of SIDT instruction, or every debug exception, or every page fault exception, or whatever. There's a list of few dozens of events which we can intercept. So once we create this VMCB, once we fill it with our preferred values, we can call vmrun instruction. This is one assembler instruction. This instruction takes an implicit argument, which is the address of VMCB. And this instruction is similar to call, because it starts the execution of virtual machine, which now executes, just like it was a function, it executes until some event occurs, event which we would like to intercept. So let's say we wanted to intercept, I don't know, page fault exceptions. So the operating system here executes until a page fault exception occurs, for example, or debug exception occurs, or somebody issued SIDT instruction, whatever. And then we break into hypervisor and we continue execution from the next instruction after vmrun, just like if it was a call instruction, generalized call instruction. And we call, from this on, we call this hypervisor and we call this guest. Okay, I think this should be obvious. And this is how Pacifica works, and this is how Intel VTX works. And now we have the slides, which is the most important slide during this presentation. This is how BluePill works. So again, we start here. This is our native operating system. Let's say it's Vista. So it is doing many different things, and suddenly it loads our BluePill code. And this BluePill code, at some point, well, let's say call a BluePill function. And this function does the following. It first enables SVM mode by setting this bit number 12, then prepares VMCB in a very tricky way. The tricky way is that we need to prepare it in such a way that this created VMCB, this created VM, this created virtual machine, would be the same as the current operating system. So we try to clone our operating system into VM. So it requires some tricks. One of the tricks is that we make RIP. RIP is the 64-bit version of EIP register. We make it to point to the return instruction from this function. And then we call vmrun. Vmrun creates virtual machine, and it starts executing from this address. So it starts executing from return. So it starts executing from here. So suddenly, we were here, we were the native operating system, we called this BluePill function, and we landed here, but we are now inside a virtual machine. And we continue executing. Let's say we have here like driver entry for our BluePill, and here we like have return status successful, and the operating system is doing something else, right? Switching to other processes, whatever. But now it executes inside virtual machine. And this here is the hypervisor, because we executed this instruction and we execute here. And let's say we wanted to have a keylogger. So we said that we want to intercept every interrupt. I don't remember what's the interrupt. Some keyboard interrupt. So it executes. Suddenly user presses key, and we have this intercept, and we land here. And here we have a big switch to see what event occurred. We do the appropriate action depending on the implementation, and we execute vmrun again, and we continue our operating system. So this is funny to notice that on this slide we had native operating system, which then became sorry. We had this native operating system which then became hypervisor, and we had guest here. But here we have native operating system which became guest, and we had something which wanted to become guest but became a hypervisor actually. And the funny thing is that this operating system doesn't know that it actually became guest. This all happens on the fly. So we don't need to modify any boot sector. We don't need to take control before the operating system boots. This is very important because this means that we can create non-persistent malware with this, which means that we cannot be detected by cross-view detection, like offline analysis or anything like that, because we don't modify disk. It's not necessary. Of course, the problem with non-persistent malware is that it disappears after a system is restarted. But there are several things which should be considered here. First of all, if you consider servers, they are very rarely restarted, so this is not an issue. If we look at the Vista, the power off button actually doesn't shut down the system, it only puts it into suspended mode. And also, we've seen this Subvert rootkit, which I'm going to talk about in a minute, from Microsoft Research, which used VMware, and they actually implemented emulated shutdown and emulated restart. So we probably can do the same. I don't know, I haven't implemented yet, but we can probably do the same. So we might just get rid of, we can actually emulate all the restarts, so we can have actually our non-persistent malware to become persistent without any modifications to disk. This is something for the future. Okay, Subvert rootkit was released a few months ago by Microsoft Research and University of Michigan. It uses a commercial VMM, either virtual PC or VMware, to run original OS inside VM. And it's necessary to compare those two creations. So Subvert is on the left and Bluepill is on the right. Subvert is permanent. It needs to be permanent, because it must take control before the original operating system. Bluepill is not persistent. It works on the fly, so no modifications are necessary to disk sectors. Second, Subvert was created for standard x86 architecture. It only uses software virtualization as implemented in VMware or virtual PC. That means that it's not resistant against SXDT attacks. Like, for example, I implemented a little program called Redpill a few years ago, which can be used to detect virtual machine by just using a design issue with this. Because x86 architecture doesn't allow for full virtualization, because there are sensitive instructions which are not privileged. On the other hand, BP relies on hardware virtualization, which promises full virtualization. So Redpill-like attacks shouldn't be possible to detect Bluepill. Subvert is based on a commercial VMM which creates virtual hardware. So once you run VMware, you have this VMware network card, VMware graphics card, and etc., which of course allows for very easy detection. Bluepill uses very thin hypervisor, which doesn't intercept any I/O communication, which means that the Bluepill operating system